foreigner friends. Let me introduce myself first. I am Strong Art, and write down my name here. But I'm glad you call me Professor Strong Art. I come from China. I'm good at math and also a philosophy. But I don't want to talk about philosophy here. I study math all by myself and read many books, but I stay at home, so a lot of papers. Because of the Chinese tradition, no university asked me to do some research or give them a report like this, and even to help their teachers and students. But I want to communicate mathematics with other people, so I write articles at my blog and camera myself in the video. But most of them are using Chinese. Here is a special version for the people who speak English. I can speak a little English. As you know, my English is not very good. Maybe you think this guy's pronunciation strange. He used some baby words and make some mistakes about the grammar and so on. But I hope you don't care about that. It doesn't matter. Understanding is enough. Okay, today I will show a way to how to understand a new concept or new definition in mathematics. As we know, sometimes when we read the math book, a new definition will puzzle. I don't know why the mathematician will create such a strange definition. But that is hard, something hard for the beginner. But don't worry, I will help you. Now here is a way to understand a new definition. Now remember for letters N, L, and A. The first M is motivation, L is liver, second M is model, A is application. Now let me explain it. First, motivation. I think the motivation is important. When you see a new definition, you will think, why? Why the mathematician created a definition? If you know why, you can understand it naturally and find, oh, it's just like this. It's very easy. But if you don't know why, maybe you were puzzled. Now here is an example of the motivation. It is about the localization. Maybe you have learned it. Maybe some person have not learned it. It has another name is fraction ring. It is a very important trick in the communicative error. Now maybe you can see it like this as minus r. It can definition by, okay, let's write it at here. And the border is something small, s plus r, and the quotient with the equivalence relation. I'll write down the definition first, okay? Now look at the definition. It looks strange for the beginner. When I first learned this definition, I also find it strange. I don't find it is hard to understand. If it is not an important definition, maybe I can ignore it. I can skip it. But it is the foundation. It is the professional knowledge of communicative error. It can use again and again. I cannot skip it. At that time, I don't touch the computer and I don't go into the internet. So I must do it as a stupid way. I remember the definition and do many exercises. Some Chinese teacher often tell you use this way. They tell their students, if you don't know why, you can remember it first, then you will understand it in the future. But I think that is a stupid way, especially in math. It looks like that you threw some rubbish in the environment and you think, oh, the environment will clean itself and clean my rubbish. Maybe a little does, but if you put more and more rubbish in the environment will become dirty. This situation is like the putting rubbish in the environment. But luckily, I understand it after all. Maybe because it is a little rubbish at my brain, and my brain can clean it by itself. Why we will create such a struggle? Oh, I clean my brain. Oh, here S is a multiplicative set, okay? It is multiplicative closed and contains the 1 in the ring R. Why will create such a strange struggle? I know when R is domain, it is S minus R is a fraction field. So maybe we want to partially inverse. So I don't familiar this struggle. I'm glad to write something like this, okay? R1 S1 is R1 is S1. If we product it plot, then we can put the S outside, so get the struggle like this. Why we have not this struggle in domain? Because in the domain the S has inverse and it can jump. But in the common situation, it cannot jump. So here is a S. Okay. By the way, why we want S is multiplication stage. Maybe we have S1, S2, S1, S2. So here is the reason. And why we want S contain 1, maybe R is R over 1. Look at this. Now, so here is the multiplication of S minus R. We can do it, we want to do it, we want to have the inverse partially. If we don't have the inverse totally, we want, at least we want to have it partially. So we construct this struggle. But as we know, no book explain it. So made many beginner puzzles. Okay, that is the first motivation. Let's look at the second level. When we see a concept, we have a different level to understand it. Maybe the concept is constructed step by step. So like we know group first. When we're familiar with group, we can learn a ring. When we're familiar with a ring, we can learn a module. When we're familiar with module, we can learn ever. Okay? Step by step. And another situation is when we learn a new concept, we understand it in the different level. For example, when we learn a ring, we can in the element level for the beginner. Okay. When you study the first course of ever, you often treat the ring like this for any x belong to R and you discuss the ring like this. But when you study the advantage ever, you discuss the element less and less, and you use the ideas there instead of it. Okay? You often say that for any idea belong to R and and when you study deeply, you find a module is very important. Okay, you see some ring, see some module, and go back to the ring and find this kind of relation is very interesting. For example, a ring is semi-simple ring if and only if the ring R is semi-simple ring if and only if any R module is semi-simple, if and only if any R module is injective, if and only if any R module is projective. That is very interesting. So there is the lever. Okay, let me see. Oh, another example is about airport space. That is a very interesting situation. Okay. when I discuss math at the internet. One day when I say, oh, suppose a separable indefinite dimension Hilbert space. A person asked, in which Hilbert space? Is it L2? I know. First I find this question is something strange, but then I know, we understand the Hilbert space in the different levels, okay? I understand it at the, maybe I can see it at the advantage level, maybe I can see it at the average level, okay? In the average, this kind of level is nature, but in other subjects, maybe you will see some visible or vivid object, math object, and you are not very familiar with the average, some struggle like average, okay? So I understand it at the average level, and I think you give me the orthonormal basis, and even the power of the orthonormal basis, it can determine the Hilbert space in the maybe the in the level of isomorphism. I only teach the isomorphism classes, but he or she want to know which Hilbert space it is. If you want to see something variable, something vivid Hilbert space, and he can only understand. Maybe he only understand that. Okay. Now here is the example of lever. Now let's look at next the model. I think the model is very important. Some the definition are abstract. You must keep a model in your mind and let it help your thinking. Okay. Some models are examples, but not every example or model. For example, if you want to know the manifold, okay, manifold. If you want to understand the more manifold, just feel free, maybe good model, okay? Of course, the finite dimension Euclidean space like Rn is also an example of a manifold, but many of the important struggles are vanished. It is degenerate. Okay, a model is a non-degenerate example. In the manifold, we want to several coordinate systems. Okay, at the surface, we have a coordinate. We have at least two coordinate systems. But at the n-dimension Euclidean space, only one coordinate system. That is common. That is nothing strange. A two coordinate system and several coordinate systems. That is the key of the manifold. If you have a property, you can define a property in any coordinate system, and the property is keep the same, then we can define property as the whole manifold. Okay, here is a model. Another model is a parallel definition. Some definition is look the same as the other definition. Now here is the example. In the routine. Okay, Look at here is an example in the routine book. Maybe it is famous. It is famous. Maybe you have know it. Real and complex analysis. Now here is translated by Chinese. Okay. In the first chapter of Walter Routine book, Real and complex analysis, when he discussed the measurable fraction, she compared it with a continuous fraction. In some property, they look the same. And when you learn the measurable fraction, you can keep the continuous fraction in your mind. That seems the continuous fraction is a model of a measurable fraction. But by the way, I find there are differences because the continuous fraction is defined locally, and the measurable fraction is defined globally. That is the essential differences between them. Okay, and even they are relation of a model. Okay. Now at the last, it is application. Why application is important? When you know that, when you're familiar with the application, you can find, you really know, really understand the definition. It looks like when you can ride a bicycle, you know you really can ride a bicycle. Maybe you are not familiar with bicycle. America may be familiar with to drive a car. I have no car. I have only bicycle. When you drive a car, you know you can drive a car. So application is important. When you use some definition, you know you can understand it. Now, for example, as I say that before, the property defined under a manifold is application. And also you define, for example, the subgroup, quotient group, and direct sum of the group. Then you know there is a kind of application of the group. If you know you can define it in a familiar way, then you know you understand the group. Okay. Maybe some complex definitions are hard to use. For example, the catalog. Okay. How to use a catalog? It is highly abstract. Maybe here is a way. In the catalog, there is no element. If you want to say F is a suggestion, you cannot say, fx is 0 implies x is 0. You cannot say that. And you even cannot say fx is fy imply x is y. In the category, in the category, you can only see that they only have morphisms, but not elements. You can only say fg equal to fh implies g equal to h. That is the injection in the category. Okay. So here is an application of the category. You can put it in the special situation, for example, module. In fact, in the advantage module theorem, we use this more than use to use the elements to describe the injection, surjection, and so on. Okay, and many applications are like a calorie. So I will talk something about the calorie. A calorie is not you don't treat calorie as a independent proposition or independent theory. A calorie, if you want to prove a calorie, you can go back to the original theory, and you find in many situations you will find that is effective. You can easily prove the calorie from the theory, but that is only good if you want to do perfect. If you want to do it perfect, you don't look at the calorie. You can look at the theory first, then you to guess what kind of calorie will appear. Okay? You can look at the theory and find the calorie as soon as possible. Then maybe you can guess what the author is thinking, and maybe you can find some new calorie. Now this way is also used to application, and you can understand the theory deeply, and here you can understand the definition deeply. Okay, here is a way to understand a new concept. Okay, remember this for later, MLMA, when you feel puzzled with some definition. Maybe it can help you. Okay, so much for today. Bye.